all of you. You have already discussed with Professor Suman Chakraborty about some important properties of fluids like viscosity, the kinematic viscosity which is known as momentum diffusivity, then the surface tension and the capillary rise as a consequence of surface tension and density. Now, I will conclude this session of fluid properties by discussing another important property of fluid is compressibility. 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 So, I will discuss now of this property compressibility. Now, compressibility of any substance is the measure of its change in volume with respect to the applied pressure on it. This is the first basic definition. The compressibility is the measure of change in volume of any substance with the applied pressure. And in this context, you must remember one thing: the pressure and volume always bears an inverse relationship for all substances. So, therefore, with the application of the pressure, there will be always a decrease in volume. Now, different substances behave differently with the application of pressure for its change in volume. Means that for a given pressure, the change in volume will be different for different substances, or otherwise for a given change in volume, the pressure, applied pressure will be different for different substances. These differences in nature of the substances in responding to its change in volume with respect to the applied pressure is described by a property known as bulk modulus of elasticity. Probably you know this thing. And this bulk modulus of elasticity is expressed mathematically as this. It is written as E, bulk modulus of elasticity, which is defined mathematically as delta P, that is the change in pressure, divided by the relative change in volume, delta V, relative change in volume, delta V, divided by V, that means change in volume divided by the relative change in volume. Limit of this as delta V, that means this change in volume, should tend to 0 mathematically, but actually this is delta V we define as star, delta V star, as just now Professor Suman Chakraborty told, and I told you earlier in the morning session that this limit, this is the definition of bulk modulus of elasticity, the property which takes care of the differences in the response of change in volume with applied pressure for different substances. This is defined mathematically with the limit delta V should be as small as possible, not exactly 0, which should not violate the continuum. Because if it is 0 mathematically, it violates the continuum. That means delta V star is that minimum volume for this substance under concern where the continuum approach is valid. So, this is the basic definition. So, mathematically this can be written as V, okay, dP dV, that is the volume. Okay. Now, we know for a given mass of a substance, the product rho into the volume V equals to constant. The product is constant. which gives mathematically that d rho by rho is equal to minus dV by V. So, therefore, we see that we can define this bulk modulus of elasticity in terms of the definition with rho. Now, here there is one thing I forgot to tell you, that as I told at the beginning, that you must remember that for all substance pressure and volume bears an inverse relation. So, therefore, if we take delta P in its positive sense as an increase in pressure, then delta V will be decrease, a negative. So, therefore, to define a scalar property like E, we have to incorporate here a minus sign. That means, here it will be minus of delta V by V. If you cannot follow this writing, I am telling you by what, that this will be minus delta V by V. So, therefore, this will be minus by definition, because this is always negative for all substances. So, this can be written in terms of density now. Since dV by V is d rho by rho, we can write this is also in terms of rho into dP by d rho. So, therefore, this is the definition of bulk modulus of elasticity. Now, after this mathematical definition, it is clear that if the bulk modulus of elasticity is very high for any material, then what will indicate? For a given values of pressure delta P or dP here, the change in pressure, the value of dV or d rho is extremely small. That means those substances are virtually incompressible, less compressible, compressibility is very less. Whereas, if E is very less, then what does it indicate? That for a given dP, that is change in pressure, the change in volume or density is substantially or relatively high, or vice versa. For a given change in volume or density, when E is very low, then the pressure required is also low, which means that E, this bulk modulus of elasticity is very high, fluid is less compressible. And if the value of E is low, then fluid is more compressible. I give you an example. Since fluid comprises liquids and gases, for liquids usually the value of E is very high as compared to that of gases. That is why liquids are relatively much less compressible than the gases. An example I am giving for water, E equals to, I am telling, I am not writing everything here, E for water 2 into 10 to the power 6 kilonewton, this will come K kilonewton per meters square. This is the value of bulk modulus of elasticity for water. Vis-a-vis for air I write, and for air the value of bulk modulus of elasticity depends upon its pressure, and air at standard atmospheric pressure, the value is the atmospheric pressure itself, that is 101 kilonewton per meter square. So, you see that by orders of magnitude, the value of bulk modulus of elasticity for water is 2 into 10 to the power 4 times more than the air. So, therefore, water is almost incompressible, that means its compressibility is very less, while air is very much compressible as compared to water. Now, the concept comes like this. With this definition on the background, as a property of a substance, that bulk modulus of elasticity or compressibility, at the same time I must tell you the inverse of this is defined as compressibility, that is characterized by K, and this is defined as just the inverse of this 1 by E. 1 by E is defined as compressibility, which is equal to dV, that means 1 by V, 1 by V, this is coming 1 by V dV dP, this also you must know, dV, dV, V is not coming, dV dP, dV dP with a minus sign, or equals to just reverse of reciprocal of that, that is 1 by rho d rho d rho dP, d rho dP, this will be rho, this is the compressibility 1 by, okay, this is d rho, এটাকে পাল্টে আনো, this is this just checking, d rho dP, okay. So this is the definition of compressibility, that is this reciprocal of the bulk modulus of elasticity. Now the concept is like this, with this definition of bulk modulus of elasticity or compressibility, reciprocal of that, as the basic property of any substance, for example a fluid now, for a fluid, that how much to what extent a fluid can be compressed by the application of pressure, we are very much interested to know that when a flow takes place by virtue of a pressure difference or a pressure difference exists in a flow which is known as pressure driven flow, what is the change in density brought about by this pressure difference in the flow. Why we want to know that? This is because if the density in the flow remains constant, if you consider the density in the flow remains constant, but density can never remain constant if there is a pressure drop delta P. This is because that value of the bulk modulus of elasticity cannot be infinity. Similarly, the value of the compressibility cannot be 0. Here you see the value of the E and value of the K, so that dV and d rho become 0. So there will be some change in density and accordingly some change in volume. Now if this change in density is so small that we can neglect it by our engineering approximations and can make the flow with a constant density flow, our theoretical analysis becomes terrific simpler. So this is the reason for which we seek the conditions that at which the pressure drop brought about by the flow causes a density change to what extent. So let me see that. So with this thing in mind, let us see what is the change in density brought about by the pressure drop in a flow. Now we know that this will be told or this will be taught afterwards in details. As you know that for any pressure driven flow, the pressure drop delta P in the flow, the order of the pressure drop is same as the order of the dynamic head, half 1 by 2. So this 2 is not coming, half rho v square. So this is in the order of half rho v square, this is dynamic head. This comes from Bernoulli's theorem, where v is a representative or characteristic velocity of the flow, which may be free stream velocity for external flow, may be average velocity, will be average velocity for internal flow. Here we know that a characteristic velocity of the flow. So delta P is in the order of that. Now you see from your note that, as I told earlier, just go to the earlier. So this delta P, yes, you see from this that delta P equals to, from this definition here, is E into delta rho by rho. If you connect with E, it will be E into delta rho by rho. You see that E into delta rho by rho from this definition. Okay. So therefore, if I now replace this by E into delta rho by rho is very simple. Delta rho by rho writing is more complicated than the concept underlying in this here is proportional to half rho v square. From this I can write this, and one step further we can write delta rho by rho is proportional to half it will be E half, what is that, V square, V is the velocity, V square, all right, V square divided by, now I write it like this, E by rho. It is simply writing this, taking E that side. Now, this quantity E by rho root over of E by rho, E divided by rho is known as the velocity of sound in that medium at that state. So, in the medium, the velocity of sound, which we call as acoustic speed or sonic speed, with reference to the medium, that means relative to the medium, this is the equation, that the acoustic speed with relative to the medium in a medium is given by under root E by rho, which was given by Laplace, and it is known as Laplace's equation in basic physics. So, if this is so, then this can be written as half of V square divided by A square. Okay. So, therefore, we see that the change in density divided by the density means this is the relative change in density in a flow is related to its pressure through its characteristic velocity because of the Bernoulli's theorem. Since the pressure drop is of the order of dynamic head, is proportional to, almost equal to, half of the square of the characteristic velocity of the flow medium divided by the square of the acoustic speed in that flow relative to the flow in that medium, and this depends upon the state of the medium, which is designated by its bulk modulus of elasticity and rho by this equation of Laplace. Now, a quantity is a number is defined, which is the ratio of the flow velocity, any characteristic flow velocity, to the acoustic velocity with respect to the flow, relative to the flow in that medium, as Mach number, M A, which is known as Mach number, M A C H, Mach number, N U M B E R, Mach number. So, this is defined as, so therefore, we can say that delta rho by rho, that is relative change in density, is proportional to half of Mach number square, M A square. That means, there is a number, Mach number, which is the ratio of V by A, which specifies the change in density to the original density, means the relative change in density. Now, if we consider from engineering approximation that we will tolerate del rho by rho, that means density variation, so long the del rho by rho is less than equal to 0.05, that means 5%, that means the variation of density will be 5% of its original density, then as an engineer we will consider the density in the flow to be constant. So, that simplification will be done. Then if you put it here, we get a conclusion Mach number in the flow should be less than equal to Mach number, it is M A, should be less than equal to 0.33, 0.33, 0.33. So, this acts as a thumb rule that if in a flow the Mach number is less than 0.33, we can safely tell that the flow takes place with constant density. Okay? Now, let us go one step further for this thumb rule. Now, speed of sound is, you see, root over E by rho. For liquid, E is very high. So, therefore, sound velocity is very high. So, therefore, for a Mach number to cross 0.33, the velocity has to be tremendously high, which is never realized, or nobody can dream that velocity in reality. So, therefore, all liquid flow, that is why, can be considered as a constant density flow for a high degree of approximation, accuracy rather, very high degree of accuracy. Whereas for gases, because of this value of E less, the sound velocity is less. So, therefore, for gases, though the sound velocity is relatively much less because of the low value of E, but if the velocity of flow is less, small velocity of flow, then Mach number may be less than 0.33 to make a good approximation of constant density flow. For an example, for air, the velocity of sound at normal condition is 330 meter per second. So, therefore, if you multiply 330 with 0.33, you get a velocity approximately 100 meter per second for the air flow, and as a thumb rule we use that 100 meter, if the air flow velocity at the normal condition or standard condition is 100 meter per second or less, the flow can be treated as constant density flow. This is the consequence of it. Here I like to mention one thing, that this constant density flow loosely we call incompressible flow. Why? Because the effect of compressibility is ignored here, because we consider the density change is so small, below 0.5%, when the Mach number is less than 0.33, a constant density flow means incompressible flow, but this is not correct. This will be told in detail by Professor Suman Chakraborty and to some extent by me, but I explain this, I just mention this in this context, that this condition tells that the density will be constant for the flow, and a constant density flow is a special outcome of the incompressibility situation. Actually, in a fluid flow, the incompressibility of flow or the incompressible flow is purely a kinematic condition, which is defined by the rate of volumetric strain. That means rate of change of volumetric dilation per unit volume, which I will tell you afterwards, that when the, if V is the volume, then 1 by V, this is V, d V d T, that means rate of volumetric strain, that is volumetric dilation per unit volume with respect to time. When this becomes equal to 0, then the flow is considered to be incompressible, and this can be shown from the kinematics that this is nothing but the divergence. This will be told by Professor Suman Chakraborty. I just mention in this context to avoid any confusion that this is the incompressibility of the flow. A flow will be considered incompressible when its rate of volumetric dilation from the kinematic condition becomes 0, which also is equated or equals to the divergence of the velocity vector, where V is the velocity field. And a constant density flow also, this is 0 and this is 0, which will be again explained. So, constant density flow is a special class of incompressible flow. So, therefore, I think at this moment when we read compressibility as the property, then better we should take it this way, that when Mach number is less than 0.33, in that condition of the flow, the density can be considered to be constant. It is a constant density flow, the compressibility effect is neglected. Okay. Thank you. This is the compressibility. Now, we will be back at 4:15 p.m. and to take your questions, and our teaching assistant Mr. Uddipto Ghosh and
Okay, so we will in this session take up some questions and then discuss about some tutorial problems. That is the agenda of this particular session.
তুমি এক্সপার্ট সাবজেক্ট ম্যাটার এক্সপার্ট আমার কোশ্চেন নেই আমি জানি কারণ আজকে যা পড়িয়েছি তাতে কোশ্চেন হয় না কম্প্রেসিবিলিটি সম্পূর্ণ কি কোশ্চেন হোয়াট ইজ কম্প্রেসিবিলিটি আবার ওইটাই জিজ্ঞেস করা if the fluid is incompressible then what is
RCID 1308.
Yes sir, 1308.
Yes. Please go ahead with your question.
Sir, during the viscosity discussion of viscosity,
Yes.
that, variation of viscosity according to the temperature.
Yes.
Variation of viscosity according to the temperature, that you told that in case of gases,
Yes.
when temperature increases, the momentum of molecules increases.
Exchange of
But
momentum.
why does not it happen in case of liquid?
In liquid also that happens, but in liquid the most dominant mechanism of viscosity is not exchange of molecular momentum, but the dominant mechanism of viscosity is intermolecular force of attraction. Intermolecular force of attraction in liquid the dominant mechanism of viscosity is intermolecular force of attraction. That the effect of that dominates much more strongly as compared to transfer of molecular momentum. Because the liquid is much more compact. Okay, next question.
Okay, thank you sir.
Okay. আপনার কোশ্চেন হলে আমি আপনাকে দিয়ে দেবো এটা, তাহলে সুকুমারের কোশ্চেন হলে সুকুমারকে দিয়ে দেবো। না ওরকম ভাবে সুকুমারও কিছু দেবে উত্তর, ওরও প্র্যাকটিস হবে হয়তো ক্ষতি নেই।
RCID 1279.
RCID 1279.
Hello.
Yes. 1279.
Sir, good afternoon, sir.
Good afternoon.
Yes, sir. I want to ask the question. So, what is the significance of dynamic viscosity and kinematic viscosity?
Oh, the significance of kinematic viscosity I have repeated a few times, but I do not mind repeating again. So, kinematic viscosity means viscosity by density. So, viscosity represents the ability of a material to diffuse the disturbance in momentum, whereas density represents the ability of a material to sustain its momentum. So, it is the relative ability of a material to diffuse momentum with respect to its ability to sustain momentum. Okay, next question. RCID 1010.
Hello, sir. Can you hear me?
Yes, absolutely.
Sir, I want to ask the question in a surface tension. Hello.
Yes.
Why we are taking force per unit length? What is the logic of that?
No,
In a
because
surface tension, we are considering.
See, like if you take the section of a bubble, it is acting over the perimeter. The force is acting over the perimeter and tangential to the perimeter. Therefore, the perimeter has a unit of length. Therefore, force per unit length is logical because it is not this force is not distributed over an area, this force is distributed over a perimeter or over the bounding bounding line of the area. So, I do not know if I draw it will it be visible, but let me try to draw it and you can see. So, this is a cut portion of a sphere. Okay. Now, the surface tension force acts in this way. So, you can see that the region over which it acts is having a total span of 2 pi r length, it is not pi r square as an area. So, because it is acting over a portion of the length, expressed in terms of per unit length is a good way of expressing the surface tension rather than expressing it as per unit area.
Okay, thank you, sir.
Okay, next question. RCID 1108.
Hello, sir.
Yeah, hello.
Can you hear us?
Yeah, we can hear you.
Sir, I want to ask you that how we can differentiate density and viscosity of the fluid. Are these two parameters related with each other? Or they affect
There
each
is
other?
absolutely no relationship between density and viscosity, but of course, in an implicit way, I mean you can say that if there is a strong intermolecular force of attraction, there is a high viscosity. So, richly dense fluid in terms of molecular distribution of the medium, a richly dense fluid is expected to have high viscosity because of the intermolecular force of attraction, but again the viscosity is a total consequence of intermolecular force of attraction and transfer of molecular momentum. So, in a highly dense system, on the other hand, the transfer of molecular momentum is insignificant. So, transfer of molecular momentum and intermolecular force of attraction taken together, which decides about the viscosity of fluids, that taken together will decide what is the viscosity. So, there is no explicit linkage between density and viscosity, except for the fact that in a highly dense system you have a strong intermolecular force of attraction, and because of that the component of intermolecular force of attraction that gives rise to viscous effects will be intensified.
Okay, sir. Thank you, sir.
Okay. Next question. RCID 1020.
Good afternoon, sir.
Good afternoon.
Okay. Hello.
Hello.
Hello, sir.
Yeah.
Yeah. So my question is the relation of Knudsen number with this one, the free flow, free molecule flow, the sleeve flow, and the transition flow. Actually, I want to know the how do you determine the characteristic length when we speak of Knudsen number? Like mean free path, we know between two collisions we take the mean free. So I want to know how we fix the characteristic length while defining the Knudsen number.
Okay.
And
So
how it is related to this.
okay. So let me define what is characteristic length. Characteristic length is a length within which over which characteristic changes take place. So let us think of a pipe. Okay. Just I am giving you one example. Let us think of a pipe. Now in the pipe, characteristic change of velocity takes place from the wall where the velocity is 0 to the center line where the velocity is maximum. So radius is its characteristic length. In engineering practice, we commonly refer to as diameter instead of radius. The reason is that like diameter is a common engineering parameter and there is no logical difference because order of magnitude of radius and diameter they are the same, one is only just the double of the other. So, you have to figure out that in your device what is the length over which characteristic changes take place, and that is your characteristic length scale. So, you have to compare your mean free path with that particular length scale. Okay, next. RCID 12, okay. RCID 1080.
Hello, sir.
Yeah, hello.
Sir, my question is, it's a very basic question. Like, I want to know that what molasses, what type of substance it is. Second question is, why can't we swim inside the molasses?
Why can't
What is
we?
the reasons? Why can't swimming?
Swimming.
Yes, swimming
Yeah.
inside the molasses. Fluid mechanics.
Okay.
I want to know that, sir. What is the
Okay,
reason behind?
the first question is
Scientific reason.
the first question is like molasses is a it's a particular type of fluid which is a thick fluid which is a non-Newtonian fluid, it does not obey the Newton's law of viscosity. So, you can relate its constitutive behavior in a certain way. The other thing is that it is not totally correct that you cannot swim in molasses. I mean, in fact, in a very thick fluid you have the Reynolds number pretty low, and it is possible to have low Reynolds number swimming. Maybe as human beings it is difficult, but if you have small animals and small creatures, it can be shown that I mean those can swim. So, I mean low Reynolds number swimming is a very fascinating topic of research, and you please look into the literature on low Reynolds number hydrodynamics that available. There is a lot of material available in the internet, and you will figure out that even in such thick materials, thick fluids, it is possible to swim. Okay.
Is there like viscosity plays any roles?
Yes, viscosity plays a major role. Actually, the Reynolds number plays a major role, not the viscosity as an isolated parameter. I mean purposefully we are not going into this topic today because we will be discussing about the Reynolds number and its significance in one of the subsequent lectures, and then the things will be clear to you. Okay, next question.
Okay, sir. Thank you, sir.
Okay, thank you. 1336.
Hello.
Hello.
Hello, sir.
Hello.
Hello, sir. Hello, sir. It is audible.
Yeah, it is audible.
Sir, my question is, when we are dealing about tractive vectors, then particularly when we analyze any kind of forces, we take cubic shape. But you have taken a particular shape having 4 faces. Why it is so?
No, why? No, I have taken 6 faces. I mean, you mean the derivation of Cauchy's theorem?
Yeah.
Where,
yes, sir. Means when we are
where it was shown Ti equal to tau ij nj, that derivation?
Yes, sir.
Okay. So, I will tell you the logic. See, for the traction vector, the surface that you are referring to is arbitrary, that T with superscript eta, that eta has an arbitrary normal. We want to represent that in terms of stress tensor components where you have tau ij, and that I will have specific directions as either x1, x2 or x3. So, if you consider the 4 facet material, out of the 4 faces, 3 faces have normals along either x1 or x2 or x3, and the 4th face has normal along the arbitrary direction. So, if you make a force balance on that element, it is possible to express the force on that arbitrary plane in terms of forces on planes on 3 other planes which are perpendicular either along x1 or along x2 or along x3. That is why that 4 facet element is chosen.
Sir, it can be done on a cubic section also by taking a particular part of the cube.
If you are if you are taking a cubic section, then you are not getting any arbitrary orientation plane. You are all the planes that you are getting, thus all the 6 faces will have normal either along x1 or along x2 or along x3. Because you have taken this type of element, that what I took for the derivation, you have one face which is arbitrarily oriented in terms of its normal, and 3 other faces are having normal along x1, x2 and x3, and it makes a closed system, I mean closed volume. But if you make a cubic face, it is a closed volume with 6 faces, but none of these faces are arbitrarily oriented, all those faces are having x1, x2, x3 as normal.
Okay, sir.
Okay, thank you. Next question. One two nine five.
Hello.
Hello.
Are you able to hear?
Yeah, you are audible.
Yeah. The question is the molten steel and water.
Yeah.
When we do experiment in the steel plants,
yes,
they do with water. I did not get completely, sir. Can you elaborate on that?
Yeah, I mean you visit any steel, any R&D laboratory of a steel plant, you will see like when you are dealing with molten steel, what are the challenges in doing fluid mechanics experiment with molten steels. One is of course very high temperature, and the other is that steel is not transparent, so you cannot visualize the flow. So to get the details of flow, let us say you want to have the to understand the mixing of flow in a steel making vessel, a ladle for example. So now if you make a model with a transparent plastic, say perspex type of model, a box, within that you have water and you maintain certain similarities. So what should be the similarities between the experimental condition and the model condition? Professor Shom will explain in details in one of the chapters on dimensional analysis, that how to design such experiments so that your results based on the model will give you understanding of the prototype. But here you have to understand that it is very difficult to use the same fluid for the model and the prototype. So instead of steel you do experiments with water. Now question is that how can you extrapolate the results of experimentation with water with what could have happened with steel, and one of the reasons why it works successfully is because although the viscosity and density for water and steel are grossly different, but their kinematic viscosities are similar. Okay, thank you. One 133.
Sir.
Yes.
I am telling from NIT Agartala.
Yeah.
I am telling from NIT Agartala. I am Torun.
Oh, hello.
I am Torun Banerjee from NIT Agartala. I want to ask one question, that there is a lot of foaming problem at the molten steel and also the in paper foaming problem. There is a lot of problem. How to solve that problem, sir?
No, that is not related to the the topics that we have covered. Please restrict your question to the topics that we have covered today.
Thank you. And another one question is that you also told at the time that when blood is flowing through the artery, how to model if air bubble is enter into the blood flow to the artery, then what will be the model to diffuse the bubble?
No, I mean see, for blood flow through arteries and veins you still use the same Navier equation with the constitutive behavior of blood. We will see what is Navier's equation later on. It is not same as the Navier-Stokes equation, but I mean the constitutive behavior of blood and the flexibility of the blood vessel. These are the two parameters that need to be considered for modeling of the bubble. It is same as the two phase models that we use for modeling common industrial problems. Similar two phase models can be used. Okay, thank you.
Thank you, sir. Thank you, sir. I want to ask another question there.
একটা স্যার তিনটে কোশ্চেন কত করতে অ্যালাউ করা যায় 1325
পড়ানো হয়
দুধ হজম হয় না কিন্তু পায়েসটা খেয়ে 1166 RCID 1166 ফাঁকিবাজি করছে ধরা পড়ে গেছে
স্যার
yeah hello hello
hello sir
yeah hello
sir to get the capillary height
yes
I have to get the value of theta as well
yes yes
so how I will get the value of theta
there is a particular way in which you can measure contact angle. So what you can do is you can form a droplet on a substrate and take the image of the droplet through a camera. So that I mean there are instruments which are available. There is a particular instrument known as goniometer. So you can use the camera of the goniometer to take the image and then you can draw a tangent to the interface. You will clearly get the interface in the image, interface between the droplet and the subsurface, and you can draw the tangent, and the angle between the tangent and the solid surface will give you the contact angle. Okay, thank you very much. 1153 you are not audible. One three 1317
Hello.
hello
Yes sir.
yeah hello
Hello.
yeah hello
Sir, I want to ask you that which one is more viscous, mercury or water?
I mean what is your answer to this?
More viscous, water or mercury?
No I mean you tell yourself the answer, because this is the answer is based on common sense.
Sir, I am confused about this. Some books tells that water is more viscous, or some books I got mercury is more viscous.
Which books can you tell?
Some competition exam books.
No, please do not read competition exam books. Okay, please do not read competition exam books. Whatever you think as a common sense answer is correct. Your common sense is better than what is written in the competitive exam books. Okay, next.
Sir, next question, one question more.
Okay, one question more. Okay.
Sir, in case of fluid, when rho is constant, density is constant.
Yes.
In that case, you tell that it is not a case of incompressible flow. If density is constant, it is not a case of incompressible flow.
No, no, no. See, I have not covered this material till now. I will cover this material day after tomorrow. Okay. So if you have this question, if you have this question after that, then you come back to this question. I will discuss this in significant details. This has not been a topic of today. This is a topic of kinematics of flow, which we will cover day after tomorrow, and I will keep your question in mind while discussing about the topic, so you will get your answer.
Okay, thank you.
Okay. 1122.
Hello sir.
Yeah, hello.
Sir, I want to the name of equation del into v vector is equals to 0.
Equation?
The repeat question, I want to know the name of the equation del into v vector is equals to 0.
Del, there is nothing called del into v vector. Del dot v equal to 0, that is an incompressible version of the continuity equation, but we will discuss about that. So please confine to the topics which are covered today. I will tell you something, that there will always be certain misconceptions about many things which you have learnt in fluid mechanics, and we will try to address them one after the other as we proceed ahead. Del dot v equal to 0 is, it is not del into v, there is nothing called del into v. You could have del v, you could have del dot v, you could have del cross v, so many things are possible. So this is del dot v equal to 0, this is incompressible version of the continuity equation.
Okay, sir. So my next, what will the value of viscosity at the 20 degrees centigrade of water?
See, value of viscosity of fluids, you have to look into the table. See, if I ask you a question, what is the enthalpy of steam at 500 degrees centigrade and 20 atmospheric pressure, will you be able to reproduce that data? So how can we memorize the value of like property values at different temperatures and pressures and tell it to you? It is better that you look into the table of properties and get the value. In internet you will get it, or in handbooks and all these you will get it. Value viscosity 1316.
Yes. This continuum concept, we have read about the continuum.
Yes.
To Knudsen 201. Suppose we are in a continuum medium, and there somewhere in the continuum there is a cusp situation or the cup situation.
You are not audible. Could you please repeat your sentence? In a continuous medium, what happens?
Concept of continuum.
Yes, yes. In a continuous medium, from that you go ahead.
Yes, in the same medium, we have somewhere situation prevailing like cusp and cup. This modeling or the mathematical expression might be complicated. Can we say this? What medium? What can it be covered in a continuum medium or something like that, or anything different than this?
What is there in the medium? What is so special about this medium?
Suppose in the continuum somewhere there is a cusp situation, there is a cusp break, discontinuity.
Oh, discontinuity. Okay, please do not confuse modeling of discontinuity with modeling of continuum. Okay, like I will give you a very standard example, a very classical example of modeling of a shock wave. Okay, so shock wave in compressible fluid mechanics is a discontinuity, but like modeling of shock wave has nothing to do with modeling of like continuum or non-continuum, because you have to, I mean, if there are discontinuities, you have to make sure that you choose your elemental volumes in such a way that you can capture strong gradients in properties. Okay. So, these strong gradients may be expressed in terms of macroscopic parameters or in terms of molecular parameters. So, both will be possible.
Next question is that is in a particular we have considered initially as a element, where on the different phases we have considered the normal stresses and the shear stress.
Yes.
Now at the same time again in the next session we have considered this element like pyramidal shape of the pyramidal shape.
Yes, yes.
What was the purpose of having?
I have already given answer to this question to like one of the remote centers just now, just now. So, the answer has already been given. কিছু শোনে না। 1136 কোয়েশ্চেন করার জন্য ছুটে ছুটে আসে।
এটা 1254
পিছন থেকে আসছে, অনেক দূর থেকে আসছে। মজা লাগছে কিন্তু বেশ। আমার ফুল রাগ, ওই যে বললাম না যে স্টিমের এনথালপি বলো দেখি। না পড়িয়ে না খালি এই কোয়েশ্চেন নিলে কিন্তু অনেক ওদের
বলো এই চ্যাপ্টারে তোমাদের
কি কোয়েশ্চেন আছে। হ্যাঁ বেশি কম পড়িয়ে
কোশ্চেনটা বলো তোমাদের কোন চ্যাপ্টারে কি সেইটুকুন পড়িয়ে দেওয়া যাবে, যেমন তুমি পড়াচ্ছি, যেমন তুমি বোঝাচ্ছি সেইটুকুন তখন যদি দরকার পড়ে পড়িয়ে দেবে, সেইটুকু পয়েন্ট কাটবে তখন পুরোটা ফিলোসফিটা বলে দেবে। এরা কিন্তু কোশ্চেন করছে, আমি বলছি কোশ্চেন পাঠানো
1222 1222.
Hello sir.
Yeah, hello.
I want to ask a question in capillary rise.
Yes.
In that expression we wrote del P is equals to Pi minus Po.
Yes.
And then that is equals to rho GH.
Yes.
And then after we wrote a expression sigma 1 upon R1 plus 1 upon R2.
Yes.
So I don't understand that expression.
Sigma into 1 by R1 plus 1 by R2 has been derived in the
yes, how it is come?
It has been derived from work energy expression. It has been derived. You please have a relook into the lecture. So there the consideration was that we have considered that there is a membrane, that membrane is being stretched. So the work done because of the pressure difference across the sides of the membrane, that work is actually energizing or creating the change in surface energy.
Okay sir.
জিজ্ঞাসা করতে হবে তাই। 1286 সুকুমার একটু ফিল্টার করো, তুমি তো আরবিট্রারি ধরে ধরে। হ্যাঁ না আগে লেখা ছিল। হ্যাঁ ওই যে উঠে পড়েছে। তো সেই এবিপি আনন্দ গুন্ডাদের যেভাবে ধরে সেরকম। You are not audible. One zero zero two না তোমার তো কোয়েশ্চেন ফিল্টার করতে হবে, তুমি স্টেট ফিল্টার করে কি করবে?
Hello, good evening, sir.
Good evening.
So my basic question is whether surface tension is there in the moving water.
Yes, I mean surface tension is an interfacial phenomenon. So it is very much there in moving water.
One more question is whether there is any limitation of the diameter of the tube for the capillary working.
Limitation in? Please repeat.
The diameter of
diameter of the capillary tube. See, we derived that the capillary rise is inversely proportional to the radius. So if you make the radius very large, like it becomes the radius of say 1 meter, then H will be very small. If you can substitute properties of say common fluids like glass as a tube material and water as a fluid, you will see that the H will be very small. So you will not get significant capillary effects. So below millimeter size typically capillary I mean beyond millimeter size, rather larger than millimeter size, capillary effects will not be that significant. So micron will be good, nanometer will be even better.
Thank you very much, sir.
Okay. One three three nine. আমাদের টিউটোরিয়াল কখন হবে? এই করেই যদি সময় কেটে দিয়ে না একটু কোয়েশ্চেনগুলো বুঝিয়ে দেওয়া হবে করে দাও। করানো হয়েছিল বললে তো হবে না। 1332.
Hello.
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 Yeah.
Hello.
Yeah, hello.
Good afternoon, sir.
Good afternoon.
Good afternoon, sir. Hello.
Good afternoon.
I am asking a question. Hello.
Yes.
I am asking a question about quantum number. Hello.
Which number?
When you go higher up in atmosphere, when we go higher up in atmosphere,
yes,
the gases become very scarce.
Rarefied.
The mean part of the gases in the higher up atmosphere becomes very high. So do we apply the cardinal concept over there in higher up atmosphere?
No, beyond a critical height, no.
Yes, sir.
Okay.
Hello.
Yeah, beyond a critical height, no.
So what is the critical height? What do you mean by critical height?
I mean it depends on the rarefaction that you will get as you go higher up in the atmosphere. I mean I cannot tell you that exactly what is the critical height, but you can
Yes.
do the classification, and based on the flow classification you can figure it out.
Okay, so thank you, sir.
ভ্যালু মুখস্থ চাই। 1307. One three zero seven.
Good afternoon, sir.
Good afternoon.
Hello.
Yeah, hello.
Good evening, sir.
Good evening.
The regime has been defined based on different values of Knudsen number.
Okay.
Is it experimentally observed or anything?
See, these are first of all, these are not hard and fast.
Defined based on different values of Knudsen number.
Yes.
Is it experimentally observed? Or
Okay. Yes. Okay. Let me give you an answer which is deeper than this. these values are not hard and fast values, these are just order of magnitudes. So when you say for example that beyond Knudsen number of 0.1 something happens, that does not mean that literally it is 0.1, it is roughly 0.1, and these rough values have been verified with experiments and also have been verified with molecular simulations, that is simulations using molecular modeling concepts, not continuum modeling. Okay. 1334.
Good afternoon, sir.
Good afternoon.
My first question, when you discuss about the viscosity,
yes,
at that time velocity gradient nature parabolic. Why? It could be straight line.
No, no, who has considered parabolic? I have not considered parabolic. I mean some book that you might have read might have used parabolic velocity profile to derive the or to establish the concept of viscosity, but I am afraid that is not the right way of introducing the concept. The concept of viscosity does not depend on what is the shape of the velocity profile.
Okay, sir. My second question. Will contact angle theta
yes
vary for different material pipe?
Yes, I mean the contact angle will depend on the fluid and the solid material combination, so it will vary. Okay, thank you. Thank you. 1051. 1051.
Hello, is it audible, sir?
Yes.
Is it audible, sir?
Yes, you are audible.
Hello.
Yeah, you are audible.
Sir, the question is, how can we define viscosity for non-Newtonian fluid?
So for non-Newtonian,
a relation that.
So for non-Newtonian fluid, some concept which is used is called as apparent viscosity. So apparent viscosity means, so for example if you write a power law fluid, then you can write tau is equal to some k into theta dot to the power n, where k and n are called as consistency index and flow behavioral index. So if you write tau equal to k into theta dot to the power n, you can write it as k into theta dot to the power n minus 1 into theta dot. So that k into theta dot to the power n minus 1, that you can because it has a unit of viscosity, you can call it apparent viscosity, but it is not viscosity in a strict sense because it is not a Newtonian fluid. Viscosity is not defined for a non-Newtonian fluid.
Sir, one more question, sir.
Okay.
Hello.
Yes, yes.
Sir, one more.
Yes,
one
yes,
more
yes.
Sir, I have read about some material known as pitch. The material is pitch. I have read in a newspaper.
What is the material? I have not heard about it.
Sir, that material is pitch, sir. P-I-T-C-H, pitch.
Pitch?
Yes, sir, pitch. P-I-T-C-H, pitch, sir.
Pitch, yes, yes, yes. That is used for making roads.
Yes, sir. Yes, sir. Sir, if that material flows through a flask, then one droplet comes out in so much long time, such as 10 years or 8 years. So how can we say that that material is either fluid or that is solid?
See, the distinction between fluid and solid, I mean there is a thin line of demarcation. The thing is that there are many substances, like let us say there is a toothpaste in a toothpaste tube. So if you are applying a very little force, the toothpaste will remain within the toothpaste tube. Beyond a critical force, the toothpaste will start moving. So and when it starts moving, I mean it flows out of the orifice like a fluid. So there is always a critical stress, and the critical stress to achieve that critical stress you may have to wait for a long time. So, it is difficult really to give a classical definition of fluid to many substances which are sorts of interfaces between fluids and solids. So, they will yield after quite a significant amount of time. So, many times these kinds of materials can be called as quasi solid or meta solid type of materials, which maybe for all practical purposes will remain stable as solid for a short period of time, but if you allow a sufficient time this material will start deforming. টিউটোরিয়াল আজকেরটা আজকে করাতে হবে, করাতে হবে মানে দিতে হবে।
তাহলে ছেড়ে দাও, টিউটোরিয়াল করিয়ে দাও, তুমি আর কেন কোশ্চেন তৈরি করছো? তাহলে গো ফর টিউটোরিয়াল
1283
তাহলে টিউটোরিয়াল অফ করে দাও।
Hello?
Yes.
Hello, sir.
Yes.
Hello.
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 Yes.
So
yes,
I didn't mean very. I meant very simple thing. It was given E is equal to half rho square by half V square by A square.
Yes.
Where A is the Mach number obviously, and is the flowing velocity.
Yes.
We know that when the air flow velocity is 110 meter per second, it is taken as less than 5% density change are taken as incompressible fluid.
Yes.
But funny thing is that if I put V is equal to 0, E becomes 0. But for this case, when
for V equal to 0 this concept is not
static gas, but static gas always there will be some compressibility. So how
Professor Som will answer this question.
How can mathematical limit theorem putting or something else?
কি বলছে দাঁড়া থেকে। Hello, yes, please tell what you want to say, that you see that V square by A square is the square of the Mach number. When Mach number is below 0.33, try to understand, that means the velocity should be such that Mach number should be below 0.33. It is not the absolute velocity, but velocity relative to the sound speed. Then the density of the fluid may be taken as constant. So what do you want to know? Please tell. Hello? Hello, what is your query? Please tell. Hello?
If I put V equal to 0 in this equation, E becomes 0.
No. Why E becomes? Look, this equation does not, where you will get E is equal to 0. Nowhere it is that E is equal to 0. Delta rho by rho is proportional to V square by A square. Okay. So if V is 0, that means the fluid is at rest. That means there is no change in density at all. So therefore the density change will depend upon the applied pressure in a static fluid. But this is in relation to a flowing fluid, the fluid when it flows. So therefore this has to be a velocity greater than 0. When V is 0, it is at rest, and the velocity of flow is no way related to its bulk modulus of elasticity. Bulk modulus of elasticity is a property of the fluid, which is independent of the flow, which is related to its change in volume or density with respect to pressure. You understand that? Okay?
Yes, thank you, sir. Well,
Okay.
ম্যাডাম কিছু বলছেন নাকি? আমি ম্যাডামকে তো দেখিনি। না সেই এটা তুমি তো ওই কোশ্চেনটা রিকভার করতে পারলে না, ওই সারফেস টেনশনের সাথে স্ট্রেসের কি সম্পর্ক, এটা সুন্দর বলা
কোশ্চেন হিসেবে পাচ্ছি না।
নাও পাচ্ছিল কোশ্চেন হইতে পারছে।
না ওটা ব্যাপারটা হচ্ছে, ওটা কিন্তু ওয়ান সারফেস টেনশন causes the shear stress.
No,
Shear stress doesn't cause the surface tension. It is one way.
1267 আপনি বলে দেন 1267
Temperature dependent of surface tension causes the shear, not other.
এখন আর কি আছে? চ্যাট করা সম্ভব। 1267 খুলে দেখো না কি আছে এখন কোনো কোশ্চেন আছে 1128 BNIT
Hello.
yeah hello
Hello.
yeah
Sir, while we are using a glass of water,
yes
if I go on adding the water up to one level, that is the top level of the glass,
yes
then up to that level the concave part of the surface, top surface is there.
yes
If
yes
I again go on increasing the water slowly, the convex part appears, then again convex part appears, and then it start falling down.
Yeah,
the
yeah,
water start falling down.
yeah yeah
Why it is so? That is because of the surface tension,
Yeah,
or
yeah,
because of the other phenomena?
yeah it is because of surface tension, and in the molecular level when water comes to the top level, I mean there is always a readjustment of the forces. So you will find like when you make a not just this, you make a cup of tea or a cup of coffee and bring it to the like upper limit, upper level of the cup, you will find that this kind of adjustment takes place, and this is a molecular readjustment phenomenon, and this is totally attributed to surface tension, which in turn is a manifestation or culmination of several intermolecular forces, and that includes the van der Waals forces of attraction as well. So, it is a very involved topic of intermolecular forces, but the observation that you have made is correct and it is related to surface tension. One two one five. সুদীপ্ত আছে জিএলও আছে না নয়ডা নয়ডা হ্যালো
Hello.
হ্যালো
In capillary action, if volatile liquid we consider, then what will happen?
Volatile liquid, if you consider, you have to
Hello?
also consider evaporation in addition to surface tension effects.
Hello. Hello.
কাটো কাটো আবার টেকনো ইন্ডিয়াতে চলে এসেছে আচ্ছা ঠিক আছে 1268
Good afternoon, sir.
Good afternoon.
Good afternoon, sir. Can you hear me?
Yes, I can hear.
Sir, in rheological curve, you have stated two non-Newtonian fluid. One is called dilatant and another is called pseudoplastic. So,
Dilatant
in
and
both
pseudo
the cases we have seen it is not obeying Newton's law. Okay.
Yes.
So,
Yes.
can you elaborate these two fluid a bit, because can you
Yes,
tell me the major differences and their applications?
Let me tell you, like let us consider a polymeric solution, entangled polymer solution, and then if you apply shear stress, the polymer chains will be broken. Okay. So, the rheology will become different. This is one example. In fact, this is like a pseudoplastic example. Like for a dilatant fluid, what can happen is that if you have aggregates, then with increase in stress, what happens is that there can be pockets of fluids which are encapsulated within the aggregates, and that makes sure that the effective viscosity goes up as the shear stress is increased. So, like various things can happen, like in blood for example, like in blood, if you reduce the stress beyond a critical limit, then the red blood cell will form agglomerates, and if the red blood cell form agglomerates, then that will increase the effective viscosity. So, different fluids like polymeric fluids, blood, and I mean several types of fluids, I mean these represent peculiar rheology, and based on that you may classify them as maybe dilatant, then pseudoplastic, Bingham plastic, all these different types. I mean it is not important for an introductory lecture to go into the details of this, but at least it is important for you to like impress upon your students that if the fluid does not obey the Newton's law of viscosity, then how its constitutive behavior can be represented with one or two examples, one like mathematically and another also graphically. So, there these curves do come. Okay, thank you.
Thank you.
1220.
Hello.
Yeah.
Hello.
Yeah.
What is the concept of stress tensor?
Concept of a stress tensor I have already discussed and elaborated, but like if you have let us consider a phase where the direction normal is I xi. So, you could express the force per unit length force per unit area in terms of the index I, but the force itself has its own components. So, there is another index necessary to represent the stress. So, you require another index j to represent the direction of the force. So, there are two indices involved, one index, the first index to represent the direction normal of the phase, and the second index to represent the direction of the force. So, these two indices when they appear together and they are expressed in the tau ij notation, then we call that tau ij as the components of the stress tensor. I mean later on I will discuss and talk about the equivalence of this notation with the other common notations like sigma x, sigma y, tau xy, these common notations. Okay.
Hello. Its practical utilization in the design of fluid machines.
Yes, in the design of fluid machines, I mean there are practical applications of the stress tensor. Yes. Okay, thank you. One 1060. এই এটাই লাস্ট তুমি 8000 জনকে কোশ্চেন করতে দিলে আর
Hello, good evening sir.
Good evening.
Camera.
Hello.
I have a one doubt.
Yes.
The area is a vector quantity or scalar quantity?
Area, it depends on its representation. I mean when you are talking about the stress, then you require to specify the orientation of the area. So, you specify it by the direction normal and typically the outward normal of the area. So, in that representation the area is represented by the area times the unit vector in its outward normal direction, and that is called as area vector. Okay, thank you. So, I am afraid we are running out of time for today. So, we will stop the interaction session today, today's interaction session here. Now, our teaching assistant Dr. Sukumar Poti will update you or appraise you of the questions of today's tutorial. That means regarding the introductory concepts we have certain tutorial problems, and these tutorial problems Dr. Sukumar Poti will discuss. He will not of course solve the problems for you, these problems will be given as a homework, and many of these problems have actually been solved in the coordinators workshop. So, the coordinators of the individual centers will already have solutions of these questions, and we expect that we get a feedback on the solution of these questions from each center tomorrow, and based on that certain assessment will be made. So, I am handing over to Dr. Sukumar Poti, our teaching assistant, who will like little bit discuss about the tutorial problems. Just please go through the problem. A block of weight W slides down an inclined plane at an angle theta to the horizontal plane while lubricated by a thin film of oil. The film contact area is given as capital A and the thickness of the film is given as small h. The length of the block is also given as capital L. The terminal velocity of the block is given capital V. Assuming linear velocity profile in the film, find the viscosity of the fluid. That means your objective is just to find the viscosity of the fluid. Just given this is the inclined plane which makes an angle theta with the horizontal, that is given. Now one block is sliding down. Now here a thin film of oil having a thickness h, that is given, and it is given that is the weight of the block as W. The terminal velocity is given as V. Now your objective to find what is the viscosity of the oil of this thin layer. So how to address this problem? First you should appreciate that the component of the weight along this direction, that's the, you know, that's the, there are two components here, this angle is theta, so that will be W cos theta, and along the direction of sliding down it will be W sin theta, and along this direction one resistive force will act. This resistive force will be just the shear stress, let us write F. So first you should correlate that the resistive force is nothing other than the component of the weight of the block. So you first find the resistive force. How do we calculate the resistive force? So your objective is just to find the resistive force. So I leave it as an exercise to find the resistive force in terms of viscosity of the oil, and then you obtain the viscosity of the oil in terms of the velocity, terminal velocity, weight, angle, and the thickness of the film. So now coming to the next problem, just please go through the problem. A cylinder of radius capital R1 rotates concentrically inside a fixed hollow cylinder of radius capital R2. Both the cylinders are of length capital L. Determine the viscosity of the liquid which fills the space between the cylinders if a torque of capital T is required to maintain an angular velocity omega. So
So, just here it is given the two cylinder. Let us consider this is one cylinder. Let us, it is given that the radius as capital R1, this is as capital R2. Let us consider the inner cylinder is rotating with an angular velocity omega. So, the space between the two cylinders are filled with a liquid. Let us consider the viscosity is mu. So, here your objective to find the viscosity of the liquid that fills the space between the two cylinders. It is just like a rotating cylinder viscometer, which is commonly used to find the viscosity of fluid. What you have to do? Just for this case, a constant torque is applied, and that constant torque will be balanced by the resisting torque. So, your objective to find the resisting torque. So, how to get this resisting torque? So, you first consider an elemental area at a radius r having a thickness of dr. So, then what is the torque? Torque is nothing the shear stress into the elemental area. What is the elemental area? This is 2 pi r, L is the length of the cylinder, and r. Sorry, that's it. Again I am writing. Fine. So, from this you just get shear stress as fine. Now, again the shear stress from the Newton's law of viscosity, you can simply apply tau as mu times the velocity gradient. Now, here one thing you should keep in mind, that is here the inner cylinder is rotating or outer cylinder is fixed, and here r is taken radially outward, whereas the y is measured radially inward. That means simply we can write this is minus mu dv dr. Now, if we relate this, we can simply get mu dv dr as minus t 2 pi r square L. Now, if we integrate this from inner to outer cylinder, that means from R1 to R2, and the velocity at the inner cylinder V inner as omega R1, whereas the V outer as, since it is stationary, so 0, just again I am writing V inner as omega R1 and V outer as 0, you simply integrate and you will get the viscosity of the liquid that fills the space between the cylinders.
it is similar to the previous question.
It was just eliminated. Just please go through this problem. A uniform film of thickness h separates two discs, each of radius r, mounted coaxially. Ignoring the edge effects, calculate the torque necessary to rotate one disc relative to other at a speed of omega if the oil has a viscosity of mu. It is given that the linear variation of velocity within the oil film. I leave it you as exercise, just go through this problem. Just next problem, what is the pressure within a 1 millimeter diameter spherical droplet of water relative to the atmospheric pressure outside, assuming surface tension of pure water to be 0.073 Newton per meter. That's it is just you simply apply the formula, that's the pressure difference between two surfaces, delta P as 2 sigma by r, that is already detail discussed in the earlier class. So just I will mail the coordinator of the remote center all the answer by tomorrow, and you asked all the participants to solve the problem and show you, and you will evaluate. On the basis of evaluations, we will provide the certificates to the participants.
Okay, so we close the session.
So with this we close the session for today, and we will meet on tomorrow at 9:30. So thank you.